Welcome back. We're talking about Newton's method. In the previous lecture, we introduced Newton's method as a generalization of what we had said about gradient descent. Whereas gradient descent tries to minimize a linear approximation to our function f, we can think about Newton's method as trying to minimize a second-order Taylor approximation of our function. In this lecture, we're going to have a different view of what Newton does, and it will allow us to compare again to gradient descent and perhaps get a better idea of why it is that Newton does so much better than gradient descent in terms of the number of iterations it needs for a particular rate of convergence. So let's go back to gradient descent and recall its convergence and how its convergence rate depends on the conditioning, and in particular how it depends on the smoothness parameter and the strong convexity parameter. The gradient descent algorithm is xt plus 1 is equal to xt minus eta times the gradient of our function f of xt. And let's see how it does for an ill-conditioned quadratic, a simple case. And let me first show you what it does by drawing a picture. We've seen this picture appear a number of different times when we're talking about gradient descent. So note that I'm drawing a quadratic. These are the level sets of a quadratic. Okay, so I've drawn here the level sets of f. In other words, the contours or the lines where f has the same value. And so the smaller, the closer to the center you are, the more optimal. So somewhere where that point is probably the optimal solution. What does gradient descent do? Just looking at this algorithm, from any particular point, it moves in the direction of the negative gradient. Where does the gradient point? It points outwards, perpendicular to the tangent plane. That means that the negative gradient points inward, perpendicular to the tangent plane. So what do we see from this picture? We see that the gradient is actually not pointing directly in the direction of the minimizer, this dot. It's pointing, in fact, almost perpendicularly to it. And you can see that the more elongated I had made this ellipsoid, and the elongation is exactly, as we'll see in a moment, a factor of how ill-conditioned it is. The closer to perpendicular this negative gradient direction would be to the direction that actually would take us to the minimizer. And that's why gradient descent has behavior that looks something like that. And let's compare this. Again, this is all in pictures. We're going to do this again on the algebraic side in a second, but I think it's useful to see the pictures. Let's compare this to the setting of something that's perfectly conditioned. What does perfectly conditioned mean? If I'm minimizing a perfectly conditioned quadratic, wouldn't have to be necessarily centered at the origin, but let me just draw it that way. If I'm drawing the level sets, perfectly conditioned corresponds to something I'm trying to do to the best of my drawing abilities here, no elongation whatsoever. And what does no elongation mean? Let's pick any starting point. Whether we're here or we're here, what is the gradient point? Points outward, perpendicular to the tangent at that point. Therefore, the negative gradient points inward, perpendicular to that tangent point. And you can see that no matter where you are, that is not having this behavior that we see on the left, where for some points, the gradient might be pointing perpendicular in a way, not away, but perpendicular almost to the direction of the minimizer. In this case, we are honed in. We are pointing directly to the minimizer. So at least from the picture, we should expect gradient descent to do much better on the right. And indeed, what would the gradient descent trajectory look like? Depending on your step size, of course, it would just be going right in, no zigzagging like we see for the setting of ill condition. We see this exactly expressed in the guarantees of the rate of convergence. So recall that gradient descent for a function f, if f is beta smooth and alpha strongly convex, then gradient descent requires order beta over alpha times log 1 over epsilon steps in order to get epsilon accuracy. A lot of this course is focused on the dependence on epsilon, but let's switch our attention a little bit to beta over alpha here. And because this is exactly the picture, the difference in the pictures between the left and the right of this page. Both enjoy this linear convergence rate of log 1 over epsilon. On the other hand, the multiplier is going to be different. If I'm perfectly conditioned, that means that beta and alpha are the same. I don't have more elongation in any one direction than the other. So on the other hand, beta is always greater than or equal to alpha, because remember that beta is a quadratic upper bound to our function f, and alpha is defines a quadratic lower bound, so beta is always going to be greater than or equal to. So in other words, the best we could hope for beta over alpha is for it to be equal to 1. That's exactly what we get on the right-hand side of a perfectly conditioned problem. On the other hand, the more ill-conditioned it is, beta over alpha could grow quite a bit. So even in our results, these capture what these pictures are showing us, that, that conditioning can significantly affect the convergence rate of the gradient descent algorithm. So one question that we should ask ourselves is, what happens if we do an affine transformation? So in other words, suppose I have this problem, minimize f of x. And what I mean by affine transformation is I'm going to rescale space. Again, this is just something algorithmic that I'm going to do. So in other words, let's define x, let's define y by x equals ay, where think about A as being a positive semi-definite and invertible matrix. PSD and invertible. And since it's invertible, that means that I can also write y in terms of x. And let me use this A to define a new function. Let's define a function g of y to be equal to f of x. Oh, I want to write it in terms of y. So what's f of x? I just look up here and see what is x. It's equal to ay. So g of y is equal to f of ay. Now, because a is invertible, let's compare these two problems. Compare minimize over y, g of y, and compare that to minimize over x, f of x. And let's ask, how do the minimum values compare of these functions? And how do their minimizers compare? So let's let y star be the minimizer on the left. Let's let x star be the minimizer on the right. Question, is g of y less than f of x star, greater than f of x star, or equal to f of x star? So how do I compare g of y star versus f of x star? Can I even compare these? And you can see from the definition that indeed these have to be equal. Because if you're telling me that you found some y star where g of y star is less than f of x star, well then I could just define my x to be a times y star, and I know that g of y star is equal to f of a y star. So that means that if g of y star is strictly less than f of x star, that means that f of a y star would be strictly less than f of x star, which of course can't happen because x star, I'm assuming, is the minimizer of f of x star. So basically what we've seen, and of course the reverse argument holds, that shows that f of x star can't be less than g of y star. So these are equal, and in particular, x star and y star are linked exactly in the way that you would expect. X star equals a y star, which is equivalent to writing that a inverse of x star is equal to y star. So these two problems are equivalent optimization problems in this sense. They have the same optimal value, and the optimal solution of one determines the optimal solution of the other. And so these are very, very similar. So it's natural then to ask the algorithmic question. Knowing that these problems are equivalent in this sense, they're both convex. This is something that you should check. So since I have two convex problems, and since we just said that solving one gets me the solution of the other, it's interesting to ask, are there advantages to solving f instead of g, or are there advantages to solving g instead of a when I'm using gradient descent? In other words, the question I have here, if using gradient descent as my minimization algorithm, which would you rather minimize, g or f? You can minimize either and you get the solution for both. That's what we've just said. So which would you prefer if I'm asking you to minimize gradient descent? So let's investigate this using an example. Let me finish this question. If using gradient descent as a minimization algorithm, is it equally hard or easy to minimize g of y or f of x? Or could one possibly be easier? And again, easier, because we're talking about gradient descent, means a very specific thing. It means fewer iterations. So specifically, it means if I run 10 iterations of gradient descent on g, is that going to be better or worse in terms of how low a value, how close to minimal I get compared to running 10 iterations of gradient descent for f of x? And note that because g and f are both smooth here, I should just write that. F of x is beta smooth and alpha strongly convex. Gradient descent is completely specified. Namely, my step size will be eta equals 1 over beta. And similarly, you can derive the smoothness parameter for g, and you would take gradient according the gradient step there. So let's actually investigate this through a very concrete application. Let's let f of x equal 1/2 x transpose qx in the case where q is equal to 100, 0, 0, 1. So this is an example that is very similar to that picture I gave 2 slides ago, where the level sets are very elongated. And so it's good practice for you to be able to go from a Q like this in a simple 2-dimensional quadratic problem to drawing level sets. So I'll tell you that the level sets are very elongated. They're not elongated in the direction that I drew before. That was even rotated. But just make sure that you can go back and forth by drawing for yourselves what are the level sets of the function f of x. Okay. So we can see, however, that this is ill-conditioned. So beta is equal to 100. Alpha is equal to 1. And that means that beta over alpha, or the condition number, is equal to 100. Okay, now I'm going to define my function g. So I need to come up with a linear transformation. So let's let a equal 1 over 10, 0, 0, 1. And x equal to ay, just on the previous slide, just like on the previous slide. So that means that g of y is equal to f of ay. let's write out what G is. We can do that now. We know what f of AY is. F of x is equal to 1/2 x transpose qx. So f of AY, I just need to plug in AY for x. So this is equal to 1/2 AY transpose, which is y transpose A transpose, times q times x, which is AY. Okay, and this is easy because everything inside is diagonal. This is 1/2 y transpose times the matrix 1/10, 0, 0, 1 times 100, 0, 0, 1 times 1/10, 0, 0, 1 times y. Multiplying these three diagonal matrices, you see that we get that this is equal to 1/2 y transpose 1, 0, 0, 1 times y, or just 1/2 y transpose y. What is the smoothness and the strong convexity parameters of G? We see that G here is 1 smooth and 1 strongly convex. So whereas the kappa, the condition number for f, I'll write a subscript f so we can remember that it corresponds to alpha, is equal to beta over alpha, or 100 over 1. Alpha for G and beta for G are both 1. Therefore, the condition number kappa, subscript G, is equal to beta over alpha, or just 1. So this is, we have, with a linear transformation, turned f into G, a perfectly conditioned function. And now we can actually do gradient descent and see what happens. So for G, from any initial y0, what do we get? y1 with gradient descent is equal to y0 minus eta. Remember, what's eta? It's our step size. It's always chosen by the smoothness parameter, so it's 1 over beta, which is 1 in this case. So y0 minus 1 times the gradient of G, 1/2 y transpose, y transpose y. And the gradient of 1/2 y transpose y is just equal to y itself. So this equals to y0 minus y0, which is equal to 0, which is the minimizer. So from any y0, G converges in one single step. Gradient descent needs one step to converge. Literally as good as it gets. Let's do that same calculation for f. Gradient descent for f, of course, is not going to be that good. So from any particular x, let's say we start from x0 equals 0, 1. What does f say? Well, we get that x1 is equal to x0 minus eta. What's eta? It's 1 over beta. Beta is 100, so this is 1 over 100 times the gradient of 1/2 x transpose qx. This is my f. x0 transpose q, x0. This is equal to x0 minus 1 over 100 times q times x0. For x0 equal to 0, 1, let's see what that is. We just do that computation. Q is 100, 0, 0, 1 times 0, 1 is equal to 0, 1. Plugging that back in, we see that x1 is equal to x0 minus 1 over 100 times 0, 1, which is, again, x0, or basically 0 and 0.99. Not the optimal solution. in one step. We'll need many more steps in order to get to the optimal solution. And this is because of this ill conditioning. So what we've basically seen here is that gradient descent is not invariant to affine transformation. In other words, if we have our function f of x and g of y equals f of ay using x equals ay, then even if I start from the same point, in other words, even if I initialize at x0 and y0 is equal to a of x0, and then I look at the trajectory, I generate x1, xt, finally x star, y1, y2, yt, all the way up to y star, we'll see that x0 and y0 are linked by x0 equals a, y0 equals ax0. X star and y star are linked because y star is equal to a of x star, but the intermediate trajectory will be different. In fact, we just saw that. We saw that in the trajectory for g in this particular example, already at y1 we were at the optimal solution, whereas x1 was not at the optimal solution. It'll take several steps in order to get to the optimal solution. So what we see here is that gradient descent is not invariant to affine transformation. By transforming the space and doing gradient descent in the transformed space, we actually are going to take a different path and possibly a faster path. Again, even though we might start and end at the same location. So how can we simply summarize what we've learned? Affine transformations help. So in other words, we learned that gradient descent is not invariant to affine transformations, and also that affine transformations have the potential to greatly speed up, of course, or slow down if you choose the wrong affine transformation, and of course that's exactly our next question. We could have started from G and done a transformation and ended up with F. It's not that any transformation is going to help. But affine transformations have the potential to greatly speed up gradient descent by decreasing the condition number, kappa equals beta over alpha. Remember, this has been another theme that we've seen before. If you turn to the lecture where we're talking about variance reduction in SGD or SVRG, trying to reduce the condition number is a big reason why SVRG comes out ahead. If you turn to the lectures on accelerated gradient descent and momentum, again we see that acceleration for smooth and strongly convex problems ends up reducing the impact of the condition number. And we reduce it from kappa to square root of kappa and how it impacts the rate of convergence. So, well, at this point, we're basically there. It doesn't take much more to realize that putting these two ideas, putting A and B together, the key idea is let's do an affine transformation. Let's combine gradient descent with the right or the best affine transformation at every step. What is the right or best affine transformation? For a quadratic, we have the answer. Doing this for the simple quadratic, we basically saw that if we can find that transformation which converts the quadratic into a function which is just minimizing 1/2 x transpose the identity times x, that's what we saw when we went from f to g, then gradient descent is going to, plus that correct affine transformation, is going to converge in one step. That's the best, of course, that we could hope for. But if we don't have quadratics, we need to take what we learned from quadratics and port it over to the general function. So in the general function, what do we want to do? What is it that we want to mimic about quadratics? We want to make the condition number, the local condition number, as close to 1 as possible. So the best affine transformation is the transformation that makes the condition number, the local condition number, equal to 1. Find the transformation that locally gives us condition number equal to 1. And for a general function, this is going to be a different condition number, a different affine transformation at every single point. But for a quadratic, it was the same one. So again, a good transformation is we need to find y is equal to ax so that locally g of y has condition number equal to 1. So what does that mean? What is our condition number locally? What's our local condition number? We're not talking about a global strong convexity and smoothness parameter. So what we need and what we learned from a quadratic is that the local condition number is the largest eigenvalue of the matrix that defines a curvature. That's exactly equal to the Hessian divided by the smallest eigenvalue of the matrix that defines our curvature, which is the Hessian. So our local condition number is this. So I need to find a way, I need to find a transformation that makes, I need an A, and again note that A really is going to depend on x unless we're quadratic. So I guess I could write a small x here, but I don't want to make notation too difficult. So I'm just going to write A, but let's remember that A actually depends on x. So I need an A so that for g of y equal to f of ay, in other words, I'm using x is equal to ay as everywhere in this lecture, so that for this function, the Hessian of g of y is equal to the identity. This is what we want. So since we have our goal, let's try to move backwards, work backwards, and compute what A should be. Well, so let's work backwards to compute A. G of y is equal to f of ay. That means that the gradient of g of y is equal to A transpose times the gradient of f of ay. And that means that the Hessian of g of y is equal to A transpose times the Hessian of f of ay times A. And this gives us the following idea. Let's take A equal to an inverse square root of this Hessian. And we need to discuss this because we need to understand we know what an inverse of a matrix is, but we need to talk about inverse square root. But just to see how it will work out, if we take A equal to the inverse square root, what are we going to get? Then the Hessian of g of y is going to equal the inverse square root of the Hessian. Let me just abbreviate my notation like this, times the Hessian times the inverse square root of the Hessian, which is going to be exactly what we need, the identity. So what we really need here is key fact that if a matrix M is symmetric and has strictly positive eigenvalues, is symmetric with positive eigenvalues, then we can write down its square root. Then m to the minus 1/2 is, again, a symmetric matrix with positive eigenvalues, and it is something that we can compute. And computing that takes about as much effort as computing the inverse. Now let's plug this in and see what gradient descent becomes once we do this transformation. The slide title kind of gives it away. What is gradient descent using this transformation? So in other words, I'm going to write yt plus 1, going to do gradient descent on g, is equal to yt minus some step size times the gradient of g of yt, where now I'm using y is equal to ax, where a is defined as what we just wrote on the previous slide. The Hessian of f, I guess I should write yt, a of xt, is the Hessian of f at xt, the negative 1/2 root, the inverse square root of that. So what we find by plugging in our expression for g of y, for gradient of g of y, let's write down what that is here. And so we'll find that that what we get is, what's xt plus 1? Xt plus 1 is equal to a yt plus 1, or yt plus 1 is equal to a inverse of xt plus 1. So yt plus 1 is equal to a inverse of xt plus 1. This is equal to a inverse of xt minus eta times A transpose times the gradient of f of ayt, which is xt. Now multiplying through by a, I get, multiply by a on the left, I get that xt plus 1 is equal to xt minus eta times a transpose, gradient of f of xt. What is A transpose? A is a symmetric matrix, so A is equal to A transpose, and A is equal to the negative square root of, the inverse square root of the Hessian. If A is equal to the inverse square root, then A times A is just going to be equal to the inverse. So xt plus 1 is equal to xt minus eta times the inverse of the Hessian times the gradient of f of xt. And this is exactly the same as Newton's method, damped if eta is less than 1, undamped if eta is equal to 1. So this is, again, just our Newton's method algorithm. So therefore the summary of the slide. Newton's method is exactly gradient descent with the right transformation at every single step. The locally optimal or best transformation at each step. So these are two different views. In the previous lecture, we talked about gradient descent, about Newton's method as trying to minimize a quadratic approximation. In this lecture, we saw that Newton's method can be viewed in a different way. It's just trying to correct for the failings of gradient descent when we have an ill-conditioned problem. We're going to stop here. In the next lecture, we're going to talk about the main convergence result, and after that, we're going to give the proof. We'll pick it up then.